Welcome to this presentation on air barriers. We're going to discuss permeable and non-permeable air barriers. We're also going to talk a lot about the building science and why we would choose one over the other. W.R. Meadows is a 100 years old company. We do make a lot of air barriers and other products. My background, I have a degree in building science and a Bachelor of Architecture. I've been a registered architect since 2002. Finding and remediating moisture problems in existing buildings is a large part of what I do. So let's get into it. Meadows is family owned and operated. Our first manufacturing plant was in Elgin, Illinois. We started out creating the asphaltic expansion joint in the highways, and since then, over the last 100 years, have added in vapor retarders, building envelope projects, construction liquids, all manufactured in America. The yellow dots are our manufacturing facilities. The gray ones are our distribution facilities. This allows us to keep our quality up and ride through a lot of various trade disruptions and supply quality made American products to your job sites. A few of the many products we do make. We also have been making a major push on sustainability documentation. We are in the Sustainable Mines Transparency Catalog and EcoMeADOWS. Both of those are online platforms. Sustainable Mines also has the additional advantage of being able to export carbon data directly into EC3. Where in California, we have to account for carbon in buildings over 50,000 square feet. EcoMeADOWS Sustainable Mines is a number of different platforms you can get on that collect all of this sustainability information for you to compare as you're putting together a project. Very worth checking out. Very, very helpful stuff. Going to take a little pause on this slide here because it's a great illustration of what air barriers and vapor permeability or non-permeability will do. If you imagine each one of those dots on the slide as a molecule of water, water is a vapor, as a gas. It illustrates the way that water moves into the building assembly. This slide is showing the summertime conditions, and we have high humidity outside, and water is always going to move from more to less, and it is always going to be moving from hot to cold. Those are two laws of water vapor, and they hold true all throughout building science. So here are our learning objectives. One, I really want to emphasize when we're talking about air barriers and vapor permeability or non-permeability, we are always designing for optimum drying. Why is that? Because water vapor is always going to somehow get into the assembly, and it's always going to need to get out. So we're always going to think about the entire assembly and the permeance of all the materials in the assembly and designing that for optimum drying. Going to just go over a few of our standard terms. There's vapor permeable air barriers, and these are air barriers that are going to be impermeable to air and bulk water, that's water in its liquid form, and yet still allow the passage of water vapor. So water as a gas can still pass through a vapor permeable air barrier. Vapor retarding air barriers will stop water, air, and water vapor. So those are not going to allow the passage of water vapor. They do all look the same. Air and water, this slide basically is about the size of the water molecule. Water is a very, very small molecule. It's actually lighter than bulk air as an individual molecule. And because it's a polar molecule, it has the ability to clump up rapidly into droplets and become heavier. But you can see the size of the water molecule, the water vapor molecule, is actually smaller than the air molecules. The O2 and N2 are actually much bigger. This allows us to make a vapor permeable air barrier by controlling the size of the polymer chains or the tightness of the weave. You can actually engineer a barrier that allows the passage of water vapor, but still rejects bulk air and water droplets. The ASTM tests behind this, and there's a lot of science behind this, are as follows. ASTM 2178 tests air permeance. Now, a lot of things are air impermeable and meet this test. Matter of fact, even peanut butter spread 20 mils thick over a non-woven sheet will pass this test. The other one we're looking at is the ASTM E96, which tests water vapor permeance. That's where we're going to cut a coupon of the material and put it over a wet cup and test how much water vapor actually pushes through. ASTM E2357 is perhaps one of the most important standards in air barriers because we're testing a standard opaque wall with a few joints in it but no penetrations. And then we're also going to test specimen 2, which has mocked up penetration, and it tests the assembly, tests the insulated glazing unit assembly, it tests pipe penetrations, ducting penetrations, and standard outlet boxes as well. Passing ASTM E2357 is much more important than the other ones, which are a lot easier to pass. They're just diagnostic of the actual membrane. ASTM E2357 talks about the whole assembly. So let's talk about what a perm is. Perm is a unit that measures water vapor and its ability to flow through a material. And that's based on ASTM E96. And so one perm is 1 grain of water vapor per hour per square foot of assembly per inches of mercury. So that's a pressure differential. And 1/7,000th of a pound is 1 water grain. So there's roughly 59,000 grains of water in 1 gallon of water. So how much water is that over 1,000 square feet of envelope? The math actually looks out really tidily in this one because of the way the perm is defined. At 0.04 inches of mercury, which is the normal load that an air barrier is subjected to, at 10 perms, you're going to get 0.4 gallons per hour of wetting or drying potential. Now, in reality, we're never going to see that much on this chart. But as you can see, as the perms go up, so does the wetting potential as well as the drying potential. Vapor barriers and air barriers are not one way. They always work both ways. So as we increase impermeance, we increase wetting potential, we also increase drying potential. As we decrease permeance, we decrease wetting potential, but we also decrease drying potential. Mr. Carrier invented air conditioning, but that may not be his coolest invention. The psychrometric chart, where he actually charted the relationship of temperature and humidity, is one of the cornerstones of modern building science. And we can see on this chart that as we approach the right side, temperature is rising, and the curve is the amount of water vapor in the air. And then on that right-hand side, there's a scale, and that is actually our water vapor pressure. So as we increase in heat and humidity, the actual vapor pressure is going up. The other thing you can see on this chart is that between 65 and 70 degrees Fahrenheit, the ability of air to hold moisture increases rapidly. When we have warm air, it's able to hold a lot of water. And as the air cools, it is able to hold less and less water. Very important concepts to understanding. Vapor retarders are typically, we're going to be talking about vapor retarders as water vapor retarders. And that's a material that's going to resist the passage of water vapor. It'll have low water vapor permeance. Vapor barrier is a term that we don't use anymore. It was used as a class 1 vapor retarder interchangeably, but it's actually technically not correct because we don't really have anything in practical building science that's ever become the true vapor barrier. And the code defines vapor retarders by classes. The class 1, which is 0.1 perms or less. Class 2, which is kind of a medium permeance, 0.1 perm to 1 perm. And class 3, which is 1 perm to 10 perms. I'm just going to say here that no correctly installed vapor retarder is air permeable. So what's in a name? There's many things that the industry will call air barriers. Air and vapor barriers, AVBs, air and water barriers, air and moisture barriers, weather resistant barriers are also sometimes air barriers. But in building science and in specifications, we should always be using the term air barriers to be very specific about what we're intending and what the function of the material actually is going to be. Here are the master format specification sections, and you can see that fluid applied membrane air barriers can either be in the same section vapor permeable or vapor retarding. Spray foam air barriers have their own section. Board product air barriers also have their own section. Plastic sheet air barriers have their own section. It's very important that we keep like air barriers in the correct section when we're specifying, and that we don't try and lump them all together in one specification section where they don't belong in, because the different ASTM tests and standards apply differently and these all have different properties. They all can perform the same, but they do require their own specification sections in order to have real clarity. So permeable versus non-permeable, which one do I specify? Do we do a permeable that allows the passage of water vapor, or do a vapor retarding one which is going to stop everything? Well, the answer is that it's going to depend. It's going to depend on a lot of things. You're always going to want an air barrier to stop bulk air, because bulk air is able to transport an awful lot of water vapor as it conducts its way through. And they're always going to be water resistant. We still have these two categories. to choose from. And that depends on many, many factors, including your building type, your intended use of the space. A natatorium is going to have different requirements than office space. Your geographic location. The geographic location is going to determine your climate. Do you have warm, wet summers? Do you have cold, dry winters? Are you living in Southern California where it's nice all year round? All these things make a big difference in whether you're going to choose a vapor permeable or non-permeable. And the code actually suggests permeability versus non-permeability based on your geographic location. Your construction material choice is also going to have a major impact because we're always specifying our vapor barrier as part of an assembly. The wall-to-window ratio, glazing is vapor impermeable. And also where you're going to locate that air barrier in the wall is going to have a major impact on your choice. Again, my pro tip for you is that water is always going to move from hot to cold. It's always going to move from a higher concentration to a lower concentration. Most of the time, the thermal gradient is going to control. So the higher your delta T, if you have a high delta T, it's going to indicate the need for a vapor retarder. Also, if you have a high humidity gradient, it's going to indicate the need for a vapor retarder. High delta T and high humidity gradients indicate greater vapor drive or greater vapor pressure. And that's actually how we calculate vapor pressure. But we're always going to be evaluating the whole assembly. What is the type of air insulation? Is it a vat insulation? Fiberglass vat or mineral wool vats are very, very vapor open. They're also air permeable. You have a ton of drying potential. Open-celled foam plastics are vapor open. Closed-celled foam plastics, especially over an inch thick, inch and a half thick, tend to be actual vapor retarders. And so we're going to also talk about the location of where these are in our assembly. Water vapor permeance of all of your materials needs to be understood in order to effectively understand what we're going to choose. Are we going to choose vapor permeable or vapor non-permeable? In building science, we have 4 layers to control the environment between the outside and the inside. We have our air barrier. That controls the passage of air and keeps air leakage from entering the building. A building that has an effective air barrier is typically going to have a third less mechanical load on it, saving a lot of energy, because air leakage is one of the largest causes for loss of energy in a building. We're going to control bulk water, we're going to control precipitation, rain, any bulk water with some sort of waterproofing or water barrier cladding that's going to shed it, roofing that's going to shed the water away. We also have to control water vapor. We have to understand water vapor and its impact. We have vapor retardant layers, and we also have thermal control, where we're going to try and control the temperature gradient in the assembly. You can actually combine a lot of these different control layers into one material, and they can be combined into one material. You don't need a separate material for each one of these 4 control layers, but you do need to understand the function of the control layers. So the location of the primary thermal layer is very, very important. The best choice in all building climate is to put all of the insulation outboard of the cladding or outboard of the sheathing behind the cladding. That is the perfect wall. In the perfect wall, we would place a vapor non-permeable air barrier directly in contact with that insulation over top of the sheathing. And that assembly is going to work everywhere. We don't always have that option when we're putting together a building. Sometimes it's just too much insulation to put outside and it's technically not feasible. But if you can do that, that is the absolute best way to get it from building science. And that's really actually where we're trying to drive the whole industry as an industry, talking about building science. The center assembly typically requires a vapor permeable air barrier because we have our insulation inboard and our sheathing has then wetting potential because it can get cool and can have condensation. And so we typically are also going to want an air gap there between our cladding. And here it's shown with a masonry veneer. Sometimes it can be a rain screen or say vinyl siding or aluminum siding or wood siding. So we're going to put an air gap there to allow for water to have drying potential there. And the last one, if we're putting some continuous insulation outboard, there's typically a code minimum of how thick that insulation could be. And typically that is going to be at a point where that insulation is going to be vapor non-permeable if it's a foam-based insulation. And so we're going to want to put that in contact directly with a vapor non-permeable air barrier so that we have all that vapor non-permeability all in one place. And we're always going to be trying to have as much vapor openness, always increasing vapor openness towards either side so we can have true drying potential. We're also going to really aim to keep moisture sensitive wall components above the dew point. And this is why we have continuous thermal insulation. Continuous insulation prevents that cladding from getting to the dew point, especially when it's on the exterior side. So it also limits condensation. Insulation was brought into building science and into building practice initially to control condensation. And that is the largest argument that anyone can make, if you think about it, for continuous insulation. We're always going to also understand that the air barrier is your last line of defense against air, water, and vapor infiltration. It's also going to be typically the most non-permeable in most assemblies. We're going to locate that towards the center of the wall assembly so that we have drying potential to either the exterior or the interior. This is one of the things that I learned in building science classes, and it's called the 40 rule. When your interior conditions are 70 degrees Fahrenheit and 35% relative humidity, your dew point is going to be approximately 40 degrees Fahrenheit. So we're going to try and keep our sheathing above 40 degrees Fahrenheit. Why? Because that's the dew point. We want to keep water from condensating on the sheathing because it's very, very difficult to get the water off the sheathing. That is also the basis of why we have a certain amount of continuous insulation outboard of that sheathing required by code. So I want a permeable air barrier through the wall from breathing dry. Well, that's good. And it works well in climates where it's warm and dry, and we're going to have drying potential then through the wall, but we also have wetting potential through the wall. Vapor permeable air barriers are not appropriate in high humidity, high thermal gradient climates. So we're going to mostly see these vapor permeable assemblies in places like Southern California, where you have very, very low vapor drives. If you're choosing vapor non-permeable, that's typically going to be where you have that continuous insulation exterior side, and your exterior insulation then is typically going to have less than 1 perm, or where wall components inside the wall are moisture sensitive. When we have hybrid walls, sometimes we do choose a vapor permeable air barrier to increase our drying potential. But if our continuous insulation is as required by the energy code and will keep that sheathing above 40 degrees, you're typically better off still with a vapor non-permeable air barrier covering your cladding. So if you look at the map, it suggests very strongly that in the white part of the United States, we're always going to be putting vapor non-permeable air barriers. We always have to control water vapor in that white area there. The gray area is mixed. And then when you get down into the dark gray area where you have the hot, humid climates, again, you're going to have high vapor drives. Typically, you're going to be wanting to have a vapor non-permeable air barrier in those places. Now, there is an engineering pathway there that if you do the analysis, you can prove that you're not going to have a lot of water vapor collecting inside the wall cavity, that you can do whatever is appropriate to that analysis. The prescriptive pathway there is typically you're going to see vapor non-permeable in the white area of that map there, and vapor permeable over there in the southwest. So what we want to do is we want to avoid the double vapor barrier. And people typically get in trouble with this when you have interior finishes that have low vapor permeance. The code actually says that if you have a class 1 vapor retarder in your wall assembly, only class 3 vapor retarders should be used on the interior side of frame walls. And just reminding you that if you're going to use 1.5 inches of XPS or 1 inch of polyiso or SPF insulation, spray foam insulation, those are typically going to be less than 1 perm, which qualifies them as at least class 2 vapor retarders. So this is another reason that we are not seeing a lot of 6-mil polyethylene put in behind the drywall sheathing anymore, because that would give you the double vapor barrier. So the mechanism behind this is that the center of the wall assembly is typically going to be one of the coolest places. And what does water move? Water always is going to move from warm to cold. And if the center of the wall assembly is cooler than the outside or cooler than the inside, you're going to have water moving towards there. If water can move towards it, we also want water vapor to dry out. This is another reason we have an air barrier, because the air barrier is going to be 100 times more effective at keeping water from entering the assembly, because we're not going to have that convective flow of air through the assembly with a sealed air barrier. Then we're only dealing with the vapor drive, which is actually much less water potential. We would have no interior vapor barrier when your exterior insulation is less than 1 perm. We are avoiding vapor retarding interior finishes. Vinyl wallpaper is a non-permeable surface, and we see that sometimes in hospitality, in hospitals, some places like that. That can really, really mess you up. If you do have vapor barrier finish inside of your building, you do need to consider vapor permeable. So you have true drying potential all the way to the outside. And you want to make sure that continues throughout the assembly. So it also limits you to the type of insulation you can place on or in that assembly. So a little chart there that shows you what kind of R values would be required for continuous insulation to be applied over ventilated cladding. That's based on the 40 rule. You want to coordinate with your interior design team when these conditions exist. You just want to make sure that everything in the wall section really is being more vapor open towards the inside or more vapor open towards the outside, so you have drying potential. So we're not trapping water behind low permeance materials. Typically, on the cold and winter side of thermal insulation, where we have no continuous insulation, you would want some vapor permeability, or when the perm rating of the exterior continuous insulation is above 1 perm. When we're talking about these board-based sheathings, we're also talking about an air barrier that is actually, in reality, going to be a membrane type assembly because it's based on the lashings and tapes that we apply onto it. And we want to be able to seal up the edges, the bottom edge, the top edge, edges where it needs other windows or penetrations. If you don't do that, you can get into a problem with 3D air networks, and you might think you have an air barrier, but you don't. You can use a vapor permeable air barrier with insulation ratings below 1 perms. Yes, you can do that. But in the perfect wall, where you have all that exterior insulation, we're typically going to want a vapor non-permeable. But again, you can see we're placing it in the center of the wall, trying to maximize our drying potential. The air barrier is going to stop that air transport of water. And so we're only dealing with vapor pressure. Once you're only dealing with vapor pressure, you typically are going to have good drying potential for the inside and the exterior. What happens when your vapor permeance is too high? Many building science organizations are going to tell you that 50 perms seems to be about the ceiling. The sweet spot in the industry is 10 to 33 perms. Why is that? That's because the higher your vapor permeance, that's also your wetting potential going up. And we're trying to limit the amount of water vapor entering into the assembly at any given point. So the sweet spot tends to be between 10 to 33 perms. We always have to worry about first water migration. If it can get in, it can get out. That's the idea there. If you do have vapor permeable insulation and vapor permeable air barrier, you can have that potential to have water entering into the wall cavity. I would tell you that insulation tends to be moisture sensitive or can be a reservoir cladding when it's near moisture sensitive materials. So if you have wood framing, you might want to avoid that. If you're still unsure of your choice, there is the option of doing a WUFI analysis. This should be done by a building scientist because WUFI analysis are typically a very expensive software to run, and you have to be very, very specific with the inputs. Building scientists familiar with your climate will be able to put the correct inputs into the analysis. What it's going to tell you typically is that the perfect wall and having enough continuous insulation outside and having a vapor non-permeable air barrier wherever you have high vapor drive potential is going to still be the right choice. If you do have some concerns or you have an unusual situation, doing the WUFI can be warranted. There's always some unique conditions and applications. The subarctic regions and Arctic climates, equatorial climates are different. Walk-in freezers are always very, very carefully designed because these are areas where you have high potential for vapor drive, because the higher the thermal gradient, the higher the vapor drive, right? The higher the relative humidity, the higher the vapor drive. For getting into detailing now, there's always something to worry about. And one of the biggest things to worry about also is wall anchors. When there's any cladding on the building, we're typically going to be penetrating the air barrier. The best is to be able to apply the air barrier around these, and the best is to have these be thermally broken. So a thermally coated two-sealed anchor is going to perform the best. When you have certain types of air barriers that you may think are vapor non-permeable, it's particularly brick ties, the masons typically tend to move these around to align them with your masonry veneer, and that creates little micro cracks around them. It can create a pathway for water, and you can actually see ice build up on the cladding, and you can see moisture moving through at those points. One of the most important things about any air barrier is that you're having full continuity. Why? Because we're going to try and stop moisture leak through the movement of air. And air is one of the biggest things that can transport. If you remember back to the psychrometric chart, warm air can hold a tremendous amount of water. The inside of that wall assembly is always going to be cooler, typically, and so it has potential for condensating out inside of the wall assembly. Once it's inside the wall assembly as a droplet of water, it's very, very difficult to move out. It's very worthwhile thinking through the anchoring situations for your cladding and making sure that the air barrier has integrity once the assembly is all put together and the contractor understands the necessity to keep that assembly airtight. Many materials have different permeance properties. Gypsum wallboard has actually got a varying permeance depending on its thickness, and also sometimes depending on the relative humidity, because kraft paper is the original smart vapor retarder. It becomes more vapor open when in the presence of high humidity. Plywood sheathing and OSB sheathing also open up in the presence of humidity. Plywood is a lot more able to do this because OSB tends to be put together with resins, which lowers its vapor permeance. But these will actually have varying permeance properties. So you would be looking at them when you're designing at the low end of those spectrums, making sure that your numbers are all lining up to align with maximum drying potential to either the interior of the assembly, interior of the space, or the exterior. There's just a little chart there showing how, as humidity rises, half-inch plywood is going to actually be much more vapor open in humidity than OSB. And also showing how polystyrene and 6-mil polyethylene retain their vapor permeance. So any of these homogeneous plastic-based materials are going to be continuous in their performance and their vapor permeance. The wood-based or the cellulose-based materials are going to increase in their vapor openness. There are also polyamide films, smart vapor retarders. They also open up in the presence of humidity. If you have to have a plastic vapor retarder for some reason in your assembly, I would recommend a smart vapor retarder so that it can open up if water gets into that wall and dry out. Those would be the polyamide films. By and large, we do recommend the elimination of the interior poly vapor retarder. And I'm just going to talk a little bit about why that is. The biggest reason is it's very, very low vapor permeance, and we have a lot of potential for water to get in through air transport and through defects in the air barrier, through defects in the construction. It's also very, very difficult to seal. One of the reasons we try and put the air barrier on the exterior cladding as penetrations are coming through as we're installing the air barrier are easy to seal up, and we can flash those, we can tape around those, we can seal those. The interior vapor retarder gets put up, and the interior finishes come. The electricians come and add more light switches, cutting holes in it, perforating it. And when we see these poly vapor retarders put up, they're being put up with lots and lots and lots of staples, right? So that's putting lots and lots of holes in. The interesting thing about vapor drive is that vapor drive is a distributed load. It's an even pressure. Vapor pressure is an even pressure. So think of that as a distributed load. So a 5% compromised vapor retarder is still going to be 95% effective. If you introduce air pressure differential, that changes that game completely. And now it's asked to be an air barrier to stop the passage of convective currents, which carry moisture into the assembly. And that is why we tend to move away from these poly vapor retarders, because they don't work as an air barrier. They tend to trap moisture in most assemblies. 100 times more water vapor is carried through a wall assembly by air leakage, or a hole in that wall, or a gap, than by vapor diffusion. So that's why we advocate for air barriers to stop that bulk air leakage. It is the most important aspect of the air barrier system. This is also why we try and couple vapor permeance with the air barrier, because we have to have a continuous air barrier for it to be effective. And so we would have to have that permeance also related to that. It makes it a lot easier to do. Here's a chart that just shows you a couple of different perm values of various things. And you can see that as you're adding insulation, it makes a lot of sense from a building science perspective to put that XTS insulation on the exterior side of the sheathing and on top of a vapor non-permeable air barrier. You can see why that is, because a lot of our interior materials, which become moisture sensitive, then have that permeance that they're going to dry out. You can also see where that 6-mil poly vapor barrier is going to give you that double vapor barrier condition, which is why we ended up with a lot of mold problems in the early 2000s, and why we abandoned the poly vapor barrier in the first place. Again, you can also see at the bottom how low the permeance is for vinyl-based wallpaper. So, it's another very thing you have to be very, very careful about. You're always going to be designing for maximum drawing. We're always going to want that vapor profile to be opening up towards the inside, and we're always going to be wanting to be opening up to the outside. Typically, the most moisture is going to be coming from the exterior. If you have a stucco cladding, if you have a drainage cladding, it's draining water away. There's always going to be some liquid water coming through that. We're going to control condensation with continuous insulation, keep that sheathing above 40 degrees Fahrenheit. And we're also going to be trying to keep water away from our moisture sensitive materials, which are typically going to be the structure and inboard of that. It's never a question of when your wall gets wet. They always are going to get wet. That's why we are always advocating for maximum drying ability. And again, we're looking at this wall section as a whole assembly and also going from floor to ceiling and looking at all those details, the rim joist detail, where it meets the glazing units, where it meets the roof. One of the most failed joint, in my opinion, in building science is the wall to roof connection. And that's because that's so difficult to seal due to construction sequences. It deserves a lot of thought there. Because the air barrier, if you think about it, has to be a continuous line around the building envelope. So we're doing the red pen test there. We're going to put our red pen down there. We're going to draw our red pen line, and we're going to come across the lid of the building, either the roof membrane or at the ceiling, and then come back down the wall. And a lot of people do this successfully at the 1/8 scale or the 1/4 scale. And where it'll typically fall apart is at those connection details where you're at 3/4 scale or 1.5 scale. And you actually really have to make sure that those flashings that connect the various control layers up and give you that continuous air barrier around the building envelope itself are truly continuous and that there's not little gaps there. Another typical thing that I see is you have to think those detail through in 3 dimensions, right? So we look at it in a section, but if you have strips of flashing, those ends of those flashings that overlap also need to be sealed well to the end, the other part of that flashing. So it is truly continuous, so you don't have a little end run for air leakage. Air leakage, again, is our major cause of moisture in the wall assembly. And climate zone and region, again, are going to be large drivers for achieving air barrier permanence. Again, we have an example of the perfect wall. You could have that as a vapor open air barrier there if you had low vapor pressure, right? So if your exterior air temperature is going to be 70 to 80 degrees almost year round, and you're going to have relatively low humidities, and your interior conditioned space is going to be 70 degrees roughly year round, you're going to have very low vapor drive. So that would be an indication that you could have vapor permeable air barrier there if you so desired. But you could also put in that perfect wall assembly, because the insulation is entirely outboard, you could put a vapor non-permeable air barrier there and still be successful in those climate zones. And there are other applications of this where we have to consider drying. This slide here shows the outside of a semi-conditioned space, and it's a CMU wall. And on the other side of that CMU wall, what you can't see is there's a boiler room. What is a boiler room typically? It's high temperature, and it can be quite relative humidity, can be quite high. So as that high humidity, as that vapor drive is pushing through that CMU wall assembly, what was happening there is it was condensating out inside the block, dropping through the cores and collecting at the base of that wall. That's an interior wall. That's not frost damage. That is all vapor drive. So what you can see there is the white on that block. That's efflorescence. Efflorescence is salts, and those salts were traveling through the masonry and building up underneath that semi-non-permeable oil paint that was applied to that blockwork, and it was unable to dry out. As you get an increase in efflorescence behind the surface, you also get something called osmotic pressure. Because water is a polar molecule, it's attracted to salts. As those salts and water molecules combine, they expand and can exert up to 3,000 plus PSI pressure, which is enough to blow the face off of that. The answer here was a vapor non-permeable air barrier applied to the inside of that wall assembly to keep the vapor drive out of the wall. And that's what we did on that boiler ring to fix that problem. Moisture sensitive details, again, need to be considered. Masonry, stucco, those are moisture storing, they're reservoir claddings. They have medium permeance. They have medium porosity, which means that when they get wet, they hold water for a period of time. That's going to create a high humidity environment there. So that requires an air gap, first of all, to separate it from conducting water into the building. And then we're going to also want to have continuous insulation to keep that cladding from getting below the dew point from that high humidity. That, again, a vapor retarding air barrier is going to be a help there, especially if we have another reservoir cladding on the inside, an exterior gypsum panel. If that is not protected from moisture intrusion, that can also collect water as a reservoir cladding and cause us further problems. So we're always trying to have drying potential. We're always considering drying potential. And we're going to try and locate our moisture sensitive materials away from vapor dry, away from high humidity, and just trying to keep the wall as dry as we possibly can. Sometimes we do have this situation where we do have the air barrier vapor retarder on the inside, much more difficult to detail. If we do have that, all of our drying potential is going to be towards the outside. We're going to want to increase that drainage plane. We're going to want to increase that vented cavity. We're going to want to make sure it's a vented cavity. We're going to want to make sure that everything outboard of that is going to have an increasing drying potential to that vented cavity there. And again, if you are in a situation where you need to understand what's happening, maybe you're dealing with an existing building that needs more investigation or has a strange wall system, maybe you need some forensics work done. The WUFI is a great tool to use, but it needs to be done by a professional who understands that the inputs going into it are going to be the correct inputs so that you get the correct output and you get the correct modeling. It will never account for application imperfections, and it won't account for materials as they age. So as materials do age, you do have deterioration in air barriers. If you have deterioration, the ability of claddings to shed water, you can have deterioration in insulation, which would lead to a lack of the ability to control condensation by keeping materials warm. So that's what the one thing the WUFI is limited by, but it is a useful tool. One important thing to keep drilling home is the air barrier is intended to be completely continuous, and we have to look at this. Failure to seal a sheathing joint, you can have sheathing that passes all your ASTM tests, and the system theoretically passes tests. But if the contractor actually fails to seal that joint on the sheathing, or that seal fails, the air barrier is going to fail, and you're going to have air transport of moisture. For detailing, where the soffit comes to the air barrier, to the wall, is another typical place where we see problems. Damage to fluid applied air barriers, you can see a handprint there. The thickness, so when you're talking about a fluid applied air barrier, it has to be applied to the manufacturer's recommended thickness in order to achieve the vapor permeance that the manufacturer says you're going to get. A thickly applied vapor permeable air barrier, if it's applied to that, can become a vapor non-permeable air barrier. And as you can see, if it's not applied thick enough, or if there's a defect in the thickness there, you will have a leak spot there. You'll have a place where it's much, much more vapor open. Just detailing around the flashings, making sure that everything's continuous, making sure that we have enough material on where we're transitioning from material types is important. Making sure that around brick ties, you don't have shadowing where material didn't get. These are all very important things. The greater number of holes and defects you have in the air barrier, it's going to increase your wetting potential. Our best practices for detailing, you're going to want to do the pre-construction meeting with the contractor. You're going to want them to understand what they're applying, how they're applying it. You're going to want them to understand that everything that you put into that detail, every extra piece of flashing, really does matter for the long-term performance. Where we have pipe penetrations, we typically want to have some sort of membrane that makes a collar on the pipe and then spreads out. So you can see the lower can corner. That's a finger flashing where someone took a sheet of material, rolled it into a tube and snipped some fingers into it, splayed it out and glued it to the wall, and then covered it up with another sheet of material. And then to finish that, they put a bead of sealant where the two materials meet and then where the material meets the pipe. Why do we do that? Because when you have surface entries for a pipe, typically that pipe is going to move differentially from the wall. And doing that kind of detailing is going to allow us to spread any force of that movement out over the membrane and prevent us from having failure. If that was just a bead of sealant around there, that's a very easy thing to break, and that's a very easy thing to fail. Round brick ties, again, very important that we have the contractor spray or apply material on the top and all the way around the brick ties so we don't have shadowing of material. Windows, door penetration, all need special flashing details. It's all stuff that the contractor needs to understand. It has to be done right. And every manufacturer of an air barrier system is going to be happy to come out and do site observations and contractor trainings on job sites. It's one of the services that we provide to keep our reputation intact and to keep your building intact. Material compatibility is very, very important. There's many different formulations to air barriers, and some of those are driven as commodity air barriers. Some of them are higher performance air barriers, but the chemistries of what that air barrier is are different, and not all of them play well together. So keeping your air barrier system specified by one manufacturer is a great way to help you assure system compatibility across your flashings, across your penetration sealants, and all of that. If you do choose to use multiple manufacturers in your air barrier system for whatever reason, please do your research and understand the chemistries behind them and the compatibilities. Make sure they are able to adhere to one another, and also that they're going to perform for the long term and not deteriorate one another chemically over time. Again, the pre-construction meeting. I can't emphasize the importance of the pre-construction meeting enough to get everybody on the same page, to make sure that the installer understands why we're doing these details and how important it is to spend those extra 5 minutes putting that extra piece of flashing on there. And site observations, again, great thing to do. Once you get to the blower door test, yes, you can still fix things, but it's so much better to go into all those envelope tests and envelope commissioning tests, knowing that you've got a really good shot at passing the first time. So in closing, air barrier permeance decisions are driven by a number of factors. The type of insulation and the thickness of the insulation, right? Because we're going to want to maximize drying potential, the location of your insulation in the wall, your interior finishes. Again, we're always advocating that interior finishes are vapor open or more vapor open than the actual air barrier itself, so we don't have a potential to trap water in a place where it doesn't belong. The interior use of the building is going to drive that decision. High humidity environments are going to require different decisions. And most importantly, vapor drive is a direct function of temperature and humidity. High temperature, high humidity fluctuations, high delta T, high delta RH is going to indicate typically a vapor non-permeable choice. That brings us to a close. Thank you for staying with me. Thank you very much, everybody. Hope you have a great rest of the week. We'll catch you on the next one.